I've been around for a while, and I've been involved in many different things and different styles of work. Mostly theoretical, some applied, but mostly theoretical, but different kinds of theory too. I started out in complexity theory. I was a student of Juris Hartmanis at Cornell, Turing Award winner for his work in complexity theory. He was one of the founders of complexity theory. And early on, I did a lot of work in that area.
The theoretical foundations of computer science are integral to us being able to advance how we process important problems today. Dr. Kozen has been instrumental in developing new theories for understanding the complexity of algorithms, identifying their ultimate limits, and helping us understand what we can and we can't do with computing.
I started off many years ago working in complexity theory, algorithms and complexity, and moved more recently into program logics, program verification, programming language semantics. What excites me about it is, I think the thing that excites me most is the fundamental nature of it. It's something that really impacts the very basis of what we do in computing. It's the meaning of computing. And I think what I work toward and what really turns me on about it is the ability to reduce very complicated things often to things that are much simpler, which gives us a much better handle on how to reason about programs, on how to express the things that we want to express, and how to manipulate them in ways that give you some assurance that what we're doing makes sense. There are many applications of program verification, of course. Very recently, I've been involved in a project with my colleague Nate Foster at Cornell and some other members of the community on a language effort called NetCat, which is an adaptation of a system that I worked on for many years called Clean Algebra with Tests, or CAT for short. And it's an application of that system to networks. So we have a language, logic, for expressing properties of networks, for reasoning about networks, for deciding whether certain properties are true. There's an automatic decision procedure. There's a complete deductive system that allows you to reason about them if you want. And we can express properties such as connectivity, reachability, loop freedom, load balancing, various things that you would like to do with networks. And this fits in very well with the recent SDN, software-defined networking paradigm, which has become quite popular in recent years. So I started working on CAT back in the 90s. I was working on a system called dynamic logic, specifically propositional dynamic logic, which is a logic that is very suitable for reasoning about programs because it has a dynamic aspect as opposed to the more static kind of logic that you see in typical math courses and logic courses. Things are, in traditional logic, things are true or false, and with dynamic logic, things can change in response to operations that you can do to change the state. So something that used to be true a minute ago might become false now, and so forth. And the logic itself gives you constructs for reasoning about that change of state. So this dynamic logic system that was invented by Von Pratt many years ago has a propositional version. And in reasoning about this, I realized that one could actually do most of what you wanted to do with a much simpler system. So this was, I think, a good observation that allowed us to simplify the system that we use to reason about the same sorts of things. So I came up with a system called Clean algebra, which is essentially the algebra of regular expressions, Many viewers will understand what that means. And it's with the addition of Boolean operations. So with that, you can encode various programming language constructs, if then else, while do, while loops, various imperative language constructs. You can encode partial correctness assertions, a la Hoare logic. It subsumes Hoare logic in a purely equational system. So you can reason using very simple logical constructs, basically equational logic, which has been known for decades how that works. So some of the biggest challenges, I think, currently working with probabilistic reasoning, there is a lot of mathematics that goes into it, and one has to be very familiar with the fundamentals, and it's a tall order to understand all this stuff and piece it together. We're often in a situation where we don't quite know exactly what the right mathematical decisions to make. So we don't know whether to design things this way or that way. Often there are some engineering decisions, mathematical engineering decisions for the logic itself, for the language itself. But by thinking about it, by trying a lot of possibilities, we have, I think, been pretty successful in narrowing it down to what we consider to be the right choices. And whatever, I think the main criterion is whatever gives us the simplest system that gets the job done. The system is implemented. It's running at Cornell. It seems to be very useful. It does what it's supposed to do. There's some competition out there, other approaches that try to address the same problems that we're addressing, and they're also quite well known and doing quite well. There's a consortium now of language design effort that we're part of, we're a member of. So I think it's beginning to come together. I think we're at a crossroads at the moment in networking. So it's this software-defined networking approach is quite young still, and we're still working out the basics of it. But I think it's eventually going to revolutionize how we deal with networks. We'll be able to have a much more global perspective and be able to optimize much more efficiently and effectively than we have before. I have been involved with the Computer Society. I was one of the founders of the LICS conference, Logic in Computer Science. It started back in 1985, I believe, was the first LICS. Either 85 or 86. I think it was 86 now that I think about it. And it grew out of some logics of programs workshops that we had we had one at IBM Research where I worked at the time, and then one that was in 83, and then one in 85 at Carnegie Mellon, and then 86 was the first LICS. I think once you have the fundamentals in place, it can be a really important guideline for telling you what to do next. If you have to make a decision about what constructs to include in your system, going down to the mathematical fundamentals can really be a big win, because they more or less, at the very lowest level, dictate what the right decisions are. And all you have to do is just understand that and realize it, and it can really do a lot to guide you in your thinking.
Some facts about Dexter Kozen. He is a former Guggenheim Fellow, the author of 150 research articles and 4 books, and he plays guitar in a rock band in Ithaca. Ladies and gentlemen, the recipient of the W. Wallace McDowell Award, Dr. Dexter Kozen.
Do what you like. Do what appeals to you most. Follow your own nose. Whatever you are most excited about, that's what you should pursue, because that's where you're going to do your best work. Number 2, stay positive. It's very easy to get knocked down or feel that you're getting knocked down by the competition. You're going to get rejections from conferences. And there's the infamous reviewer 2, or maybe it's reviewer B. Don't remember what the proper name is. It's not reviewer A anyway, it's either 2 or B. And reviewer 2 always presents themselves as an expert, gives totally random comments that are all completely wrong, did not understand what you did, and completely trashes your paper, and your paper gets rejected. My advice is don't get discouraged by that. There are always going to be people like that. There are going to be negative people who are going to knock you down, and what you have to do is just believe in yourself and keep going.
And finally, thanks to the IEEE Computer Society for all that you do for our field. I'm especially grateful for your support over the years for the LICS conference, Logic and Computer Science, which I was one of the founders of over 30 years ago. Still going strong thanks to your tremendous support. So thank you very much.